Okay, so welcome everybody for this new edition of the IPN Colloquium to celebrate the 25 years of IPN. It's my great pleasure to introduce today Claire Mathieu. She's a computer scientist and mathematician known for her research on approximation algorithms, online algorithms, and auction theory. She works at CNRS, but has been at various places before, University of Paris Sud, INS Lyon, École Polytechnique, Brown University in the States, and she has won the CNRS Silver Medal in 2019, and in 2020 she became a Chevalier of the Légion d'honneur. She also has held a chair at the Collège de France, where the most prominent French scientists organize lectures for the general public. And there she explained the important role of algorithms, both for computer applications, but also for social modeling and risks. And she stresses how important it is to know the theory to understand and model social concepts, such as the glass ceiling effect for women in academia, very important topic, I think. And she has promised to talk about that today as well. So I'm very much looking forward to her talk. So Claire, the floor is yours.
Thank you. Thank you so much for inviting me. I'm very glad to have a chance to talk about algorithms and societal problems. I will talk, I have chosen 4 examples of problems I have worked on in the last 10 years or so that are algorithmic problems, design and analysis of algorithms, but that are relevant to societal problems. The glass ceiling effect in academia, which led to a publication with Renavin, Barbara Keller, Tzvi Lotke, David Peleg, and Yvonne Anne Pignoli. Deferred acceptance algorithm for college admissions, which led to a publication with Hugo Gimbert and Simon Moras, counting people at a large demonstration, unpublished, and redistricting, which is ongoing work, but already there's a publication with Euripide Bampis, Thomas Hirard, Bruno Escoffier, Fanny Pascual, and David Solpic. Okay, so I guess I'll spend about 10 minutes on each problem to try to give some overview of the kind of questions where we can perhaps have something to bring. The glass ceiling effect in academia. So these are my co-authors. And we talked about homophily. Why? What is the glass ceiling effect? The glass ceiling effect was defined in the US in 1994 as the unseen yet unbreakable barrier that keeps minorities and women from rising to the upper ranks of the corporate ladder, regardless of their qualifications or achievements. It prevents some people, such as women or a certain race, from getting the most powerful jobs. In that work, we try to model a version of the glass ceiling problem effect in a social network, analyze it, prove some things about it, because I'm a theoretician at heart, and compare our results with empirical data. So let me summarize this quickly. For a social network, we picked DBLP. DBLP, where we have nodes for people, we have edges for people who publish together, co-authors, and the nodes have a color that corresponds to their gender. So if you look at this graph with all the computer science publications until around 2013, I think, you can see that there's a lot of blue and not that much red. See, lots of blue. And in fact, men and women are different in that graph. If you look at the induced subgraph, you can see that the subgraph induced by the blue nodes is very highly connected, whereas the subgraph induced by the red nodes is extremely sparse. It's basically a forest, or there's one, maybe a couple of unicycles, but the rest is just a forest. It's true for the blue graph, even if you just look at a sample of only, if you reduce the number of nodes. Now, nodes that are influential, what does it mean to have an upper rank? It's not a corporation. So we thought one possible proxy for being most important might be the degree, having lots of collaborators. So given a graph, we can look at the degree of the blue nodes and the degree of the red nodes, and we can see whether there's a difference. And there is a difference in DBLP. So in that case, we would say that if degree is a proxy for influence, then the most influential people, the ones on top of the hierarchy, would be the one with the highest degree. And we focused in particular on the case where we have students and PhD advisors or mentors or people who help them do their first piece of research, their first publication. We created a random model for such a graph of connectedness, student-advisor connectedness, using several social concepts that had already been pointed out by sociologists. One is the rich get richer. People are attracted to those who are already influential. This can be modeled in a natural manner by having a preferential attachment model. Another one is minority. There are fewer red nodes than blue nodes in the graph. So in the graph, over time, we have red nodes that arrive, blue nodes that arrive, and nodes tend to attach to nodes that already have a high degree, according to preferential attachment. And then homophily, what is that? This is what sociologists observed, that people tend to prefer to associate to those who are like them, similar individuals. So a red node would favor connecting to a red node and a blue node connecting to a blue node. So those three concepts, the rich get richer, homophily, and minority, those three elements pointed out by sociologists have a mathematical equivalent. You can have preferred attachment. We can say every new node is red with a probability less than 1/2, blue with a probability greater than 1/2. Selects a neighbor with probability proportional to his degree, checks the color's degree, and then if it's the same color, it accepts. If it's a different color, with some probability, it rejects and goes back to try to select a new neighbor. So when you define this model, you're sort of finding a mathematical analog of each of those sociological concepts. And then you need to define a glass ceiling. So if you look at the top nodes, the nodes that have the highest degree, do they tend to be red or blue? We say that there's a tail glass ceiling effect if, when they continue asymptotically, and we look at nodes of degree at least k, where k is at the very top, but it's high, it's low enough that there are still lots of blue nodes. What is the fraction of red nodes? We say there's a glass ceiling effect if the fraction of red nodes goes to 0. So that defines a mathematical model. With that, we prove that with these three assumptions, we have the glass ceiling effect in the way we define it. And if we remove one of those three assumptions, any two of them, then there's no glass ceiling effect. So it's sort of a minimal set of assumptions that creates a glass ceiling effect. Then we thought, all right, but is this how it happens on DBLP? Are our assumptions true? Do we observe these things? So we looked at empirically, we extracted some information from the student advisor links in DBLP. Are women a minority in DBLP? Yes. Is there homophily in DBLP? Yes. Is there preferential attachment? Yes. Is there a glass ceiling effect? Yes. So we had the mathematical model and the empirical data that went with it. And that was the gist of our work. So now 10 years later, going back to think about this, I would say that this was my first foray into that kind of problems. And since then, I've talked to a number of experimentalists who told me that when they propose a theory, so they always want to match it with empirical data, but usually they only consider that the theory has a chance of being correct if it has been verified on at least two data sets. If you only look at one data set, DBLP in our case, it is possible that there's something special about that data set, that it's not generic. Fortunately, after our work, some other people have tried to reproduce it in different contexts, different countries, and different fields, and they have found that this was also true. It could be transposed to other publications in other fields. Second, so on the surface, this looks possibly kind of nice because it's a minimal explanation. But is this explanation actually valid? We showed that those three features are necessary to get a glass ceiling effect. But did we look at the right thing? What about other reasons that might have come into play to explain the glass ceiling effect? For example, women leaving the workforce at various stages of their careers. So there are some other explanations, and a complete study with sociologically relevant would, I think, have benefited from a discussion of other possible reasons, parameters that might be competing explanations. A discussion that would say why we think this is a better explanation than that. So this, I think, was missing from our work. On the other hand, it's maybe applicable to other settings. For example, let's look at social networks. And when you choose someone as a friend, when you choose to follow someone on a social network, do you tend to follow people who think like you? Do you? Yes, I think so. Do you tend to have a tendency to follow people? Are you biased towards following people who already have many followers? That is actually quite frequent. Often people think, if this person has so many followers, then he or she must be saying interesting things. And so the result of that is, if there's a minority perspective, a minority category, then these things are enough to make the minority disappear, not be present in the very most popular people who have signed up on the social network. So this might suggest that on the social network, it might be worth trying to follow people who are not the very highest, but who are somewhat, the smaller voices, but with more diversity. That might lead to a more interesting profile of people being followed. Another question is, why do this? Why do this? And when I've given this talk in the past, there was always someone in the audience who would say, so do you have any recommendations about public policy to try to help have more, improve the status, the state of the situation of women in this context? And I have to say, the first times I heard that question, I was nonplussed. I really, just because I know how to write equations doesn't mean that I have any sense of what kind of public policy should be implemented, and I feel very ignorant of all the dimensions that might come into play. So that was my first story on my work on the glass ceiling effect. Second example, college admission in practice. From 2017 to 2019, I was involved in renovating the French platform used to do college admissions in France at a national level. I did some counseling 1 day per week for 2 years. College admissions in 2018, 800,000 applicants, high school graduates and some freshmen in college who wanted to change degrees, and more than 10,000 degrees. So they needed a platform. So let me spend a few minutes on that problem, switching gear completely. The standard choice for doing this, the standard algorithm, the algorithm of reference, is the Gale-Shapley algorithm, deferred acceptance, created in 1962 for medical interns and internships in the US. The algorithm: students apply to schools, schools rank students, students rank schools, schools have capacities. Then you iterate. Every day, each school makes an offer to the next students on its list, going from the top down up to until it has reached capacity. Then each student looks at the offers it has received and accepts the best one. And then the schools look at whoever has rejected them, that clears some spots, so they make more offers. And then you continue until it doesn't move anymore, with the twist that the algorithm is deferred acceptance, meaning when a student accepts an offer, it's not a commitment. The student is allowed to change their mind if later they receive a better offer, an offer that they would prefer. Okay. With that twist, it creates a very nice algorithm with some very nice properties. First, it runs in polynomial time. Second, it's stable. It has no blocking pair. There's no student and school who, after they have the result, look at each other and a student thinks, I wish I had been accepted to that school instead of the one that made me an offer. And the school thinks, I wish I had made an offer to the student instead of one of the ones that is coming to the school. That cannot happen. There's no blocking pair, so it's stable. Stability is important because otherwise that pair would have an incentive to come to an agreement outside the system. And so over time, unstable algorithms tend to result in things gradually unraveling. Also, this is school optimal. From the viewpoint of schools, it gives the best stable matching possible. The symmetric version, where the students make offers and the schools do tentative accepts and can change their minds, is student optimal. So this was the starting point. It was already used in the previous version of college admissions for part of the degrees in France. One question came up. Why use school optimal instead of student optimal? The student unions really wanted us to use the student optimal algorithm. Well, so one of our contributions was to look at data from the previous year and to realize that almost every student got assigned to the same school, whether you're doing the student optimal or the school optimal stable matching. Okay, so actually there's very little freedom. For almost every student, for most students, every stable matching sends that student to the same school, regardless of which stable matching is picked. But the theoretical model underlying the Gale-Shapley algorithm, when you try to use it in reality, what you quickly realize is that the ranking of schools by students is uncertain. They don't really know exactly where they want to go, and they don't really know what their preferences are. The school capacity is somewhat uncertain. The government can give more money to some schools to ask them in exchange to have a few more slots open their capacity. So there's a little bit of freedom there. The set of students is uncertain. When the students who do not graduate from high school, they will be kicked out of the system when the high school graduation information comes out. some offers might be conditional. The choice that was made had been made when I joined the team was to handle uncertainties with time. So do not ask the students ahead of time for their ranking. They just apply it to a set of schools. Then the schools do their ranking. Then they start making offers. And the students, at the time when they get an offer, several offers, at that time they have to choose which ones they reject. So they don't have to rank to know what they prefer until they actually get offers. And then you update the assignment daily to incorporate the various changes. So this immediately raises the question of runtime. I said the runtime was polynomial, but I was thinking of an algorithm run on a machine. But here, if we're waiting for students to answer questions, then we actually have an algorithm that runs in human time. One iteration takes at least a day, maybe 2 days, and we only have a few months until the semester starts. So are we sure that if we do this, we'll be done by September, by the time school starts? That was one of the questions that we were asked to answer. So one of the things we did was to create a model, run some simulations based on the previous year's preferences. And what you can see here, the two curves compare the behavior of the system as we simulated it in May, right as it was starting to make offers, and as it was observed over the summer. How many students received a proposal? How many of them got their best proposal? So we saw that actually our simulation was very close to what happened. And we also could tell that we predicted that things would converge before the end of July. The date at the bottom, the dates are May 22nd, June 22nd, July 21st, and August 21st. Convergence essentially before the end of July. Unfortunately, even though things were essentially over by the end of July, it turned out that the candidates did not know. All they saw is that the places that did not make them offers, they were on the waiting list. They could see they were, the 200th on the waiting list. And then they waited. Maybe one day there would be 199th on the waiting list. And then nothing happened. So the candidate's perception was the algorithm is not working. It's stuck, not realizing that actually the algorithm is working and it's finished. But we could not give any assertion, telling people, now you're done, it's finished, because there's no guarantee that it's finished. It always might happen that suddenly, if everybody dies that is on the waiting list, and the last one that had a proposal, then even if you're number 5,000 on the waiting list, you're going to get an offer. So we could not tell the students, we could not guarantee that they would not get an offer. And this created a lot of frustration on the student side. The other questions we had to deal with was how to incorporate quotas, tweaking Gale-Shapley to incorporate quotas of low-income students, give a little boost to low-income students, give a little boost to local students for local universities, coupling assignments to schools with assignments of dorm beds in the schools, that have a different way to rank applicants. So all these things require some additional work. This was a very exciting project. It taught me things about the distance between theory and practice, even a very clean, simple, appealing, elegant theory algorithm. There's a lot of work that goes into making it work in reality. Another thing is that the questions we dealt with, I am used to dealing with algorithmic questions. But if you listen to people, they have other questions, other worries, other issues. Some of them cannot necessarily be modeled. And so, so this was this means that really we can only be a piece, part of a team of people, because we really do not have the expertise to take into account everything that comes into play when you have a problem involving human people. Another thing, upon reflection, I realized that initially I was given the problem and I accepted it as it was given to me. But thinking back about it, there were, the roads not taken. The roads were not taken. Initially, this was motivated by the fact that there wasn't enough capacity in French universities to accept the students who wanted to study certain topics at the university. And so the algorithm is a way to deal with competition between students. Now, an alternate route could have been to give more funding to universities and increase capacities. This was not considered, and I didn't even think about it. So there are more questions that can come up if you step back and think about the problem, not just as an algorithmic problem with input-output, but as a much broader societal problem. And then going forward, I have some worries because the problem is the platform is centralized. We have implemented quotas of low-income students. There's a few lines in the code that make sure that you can do a little boost. You can tell a particular parameter to give a little boost in the rankings and therefore in the result for low-income students. Now, imagine there's a new government who decides that they want to apply national preference, give priority to all French nationals. Before, they would have had to convince every university, every school, every French institute, no matter how little, one by one, to do that. Now, all these schools, they all go to the platform. So all they would have to do would be to change, add a few lines of codes, replace the quota of low-income people by quota of French national, and raise the parameter so that all French nationals get placed, get a boost that makes them before all the other students. And there's nothing universities could do. This is really out of their power. So the centralization is a risk that I had completely not thought about. How this can be used in ways not that I had not foreseen. I realized that last year, and now it's a big worry. So that was my second application. Very exciting, but raises also worrisome questions. Third one, counting people at a large demonstration. This is in the context of the very unpopular pension reform that happened in France a few years ago. So people went to march in Paris and other cities. There were some really big crowds. And then after there's a demonstration, the police says, there were 50,000 people marching in Paris. And then unions say there were 130 people marching in Paris. Usually there's a big gap, a factor of 2 to 3 between the two numbers. So when you do computer science, you like numbers, and you see this, and there's a burning question. What is the true number? A certain number of people did march. We ought to be able to find a correct answer to that question. Okay, so that's when you're a computer scientist, that's kind of a right. That's a burning question. So this is this is one thing that I set up. I got started, and then I stopped in the middle, an aborted project. The idea is to use crowdsourcing. We film the demonstration. Then we have a video of all the people who went and, the place where we filmed. We split that video into some short segments. For each segment, we count how many people marched. Maybe we did it manually. It could also be done automatically. And then we publish on the webpage, we publish the full video, the short segments. For each segment, the local count, how many people marched in that short segment, and then the sum, the total count. And then once we publish that, it can be partly verified. That is, if someone wants to prove us wrong, if they claim it's wrong, they must show either that the short segments are not part of a long video, that there's a missing segment, or show a segment where the local count is wrong and short is short enough that this can be verified by hand, or show that the sum of the local counts is not equal to the total count. If they can't do any of that, then they can't really challenge the count. So that's what we tried to do for April 7th, 2023. This was a march against the pension reform. So first we looked for we learned the itinerary about a couple of days, a day or two before the march. Immediately, we rushed to try to find a hotel that would be positioned in a strategic location along the march. So we found one at the red spot there. Then we called the hotel, we made a reservation, requesting a room with a view, that is, a view of the march. Then, on the day of the march, we had a couple of people from the department went there to the hotel, set up some video equipment, and filmed the entire demonstration. Everybody who walked under the window. This is a picture. This is a picture. There were about roughly 100 fragments. Each was about 1 minute and 30 seconds long. Then I called up some friends, colleagues, about 60 people, I think, volunteered to do a little bit of counting. And then what you can see here is each row is a fragment. So for example, the very first row, the person who counted estimated that there were about 44 people who were marching during that segment, at least 34 and at most 54. Then the person who counted the next fragment said, in my fragment, there's 169 people. Then the next one had 718, etc., etc. So this is kind of the limit of what people are willing to do for nothing as volunteers. What we learned from this is that counting is actually not that easy. We took the video, we drew a red line. You can see the red line there on the picture, the still I took of one part. And then we added, to make it a little bit easier, we added a grid near that line. So each volunteer had to count the number of people crossing that line. But some people stopped, and did some chatting, and then they would cross, back and forth. So sometimes you had to track where people were going. Not an easy task. That's why the results are approximate. Okay, so why did we stop? We stopped because I actually got into some heated discussions with people who said, this is not the point. By doing this, you're bringing attention, the focus on the number of people who march. But that is not the true question. The majority of journalists, when they report on a march, they say how many people marched and whether any car was burnt, whether there was any violence, whether the police tear gassed some protesters. But the real question is, Why are people marching? What are they protesting about? You know, how upset are they? And this is much more, you know, this is really should be the focus. So by doing this, it's sort of a creating like a measure, an indicator of, you know, no matter what the question is, the answer is X people marched. By trying to pin down that X, it's sort of creating this as if this was the only relevant measure when it's not really true. Plus, when there's a big demonstration, some people only do part of the walk because it gets too crowded. Or maybe they go on side streets. They avoid a place that is too crowded. So there are many issues that come up that made this problem kind of the question was too sensitive and the result was too incomplete for me to be comfortable publishing it. So we kind of stopped partway. Finally, redistricting. Talk about sensitive. Okay, so this project was started when President Macron was elected. During his campaign in 2017, he said he wanted to reduce the number of parliament members, representatives in France. He wanted to have part of them elected nationally, so reduce the number of districts. So that caused us to wonder how one should partition into districts. We have 577 parliament members, so we have essentially 577 districts in France. They're called circonscriptions. In each of them, one representative is elected using 2 rounds. The choice of how you do the subdivisions can have a strong impact on the result of the election. As many of you know, there's a phenomenon known as gerrymandering that is happens in the US in particular. So we thought, we read a lot about what people do in the US. There's some theoretical analysis. What about France? It turned out that this had never been thought of as a computer science problem before. It had only been done by hand. So we initiated a study of the French situation. So first, what are the legal constraints? We go read the law. We translate that into some constraints. There has to be demographic balance. Each district has to have about the same population within 20%. Why? Because each person has 1 vote. Each vote should count the same. Second, each district should be made of 1 piece, which we interpret as should be connected. Third, it's all local. Each district is a subpart of what we call a département. If you look at the map of France here, it's colored. Each département has a color. There's 100 of them. Okay. And finally, the problem is discrete. That is, if you look at the département, here I zoomed on one. The one that is on the left map, it's blue. On the right one, I blew it up. It's subdivided into small pieces, atomic pieces called cantons. Each of them has about 20,000 people. And a district is obtained by putting together some of those cantons. So it's not person by person, it's canton by canton. So taking all these constraints into account, here are 2 possible maps for that département that has three districts, two ways to partition those into 3 districts. There are many other ways. So one thing we showed with this is that the 20% requirement for balance is actually quite reasonable. Why? For each département, we computed the total number of legal maps. And for each map, we computed the on balance. That is the district that has the highest population versus the lowest population. And we saw that there are 8 districts that have cannot satisfy the legal requirements. So you have to do some further splitting. 81 that have between 15 and 20%, 72 between 10 and 15%, etc. So we can see that the 20% condition has been chosen so that most of the départements, for most of them, there exists a legal map. Okay, so that's a justification a posteriori for that 20% bound. If we look at the number of electoral maps, we had a big surprise, which was that there's a very wide variation from department to department. It's the number of digits is 1 to 100, 2, 3, 4, 5, 6, or 7. It's all roughly the same distribution. We also tried to look at gerrymandering. So find a model for gerrymandering that is comparing the results of the 2022 elections with what the results would have been if a random map had been chosen, a random legal map. And for a given area, state, we look at the influence of the geography of a choice of map over the result. So this project, I have been going very slowly on this project because I have one worry. Since we are new to this, since it hasn't been done before us, there hasn't really been much gerrymandering in France until now. And the worry is that by doing this, we may be facilitating some future gerrymandering. So we are really tiptoeing on this study, going very slowly and carefully for releasing data and deciding what we release with what and when. In conclusion, I think I would say that these questions are, in a way, they're quite appealing because you can see the impact almost right away. They are very natural questions. They're all questions where some knowledge of design and analysis of algorithms can help. On the other hand, we are specialized in computer science and algorithms, and we don't necessarily know how to think about these questions. What is the question? What other non-algorithmic approaches might there be? And so for all those reasons, at this point, I am convinced that rather than doing things by ourselves, we really, in order to do something that has some impact, that is a positive impact, avoid negative impact, we really need help from sociologists. Thank you.
Thank you for this interesting talk, very interesting presentation. I see some applause from people. If there's any questions, just raise your hand and we will give you, give you the opportunity to switch on your camera and ask your question yourself. And maybe to kick off the discussion, I was wondering, first of all, so what you talked about, they're all applications with a very practical context, but it made me wonder, how do you find these things? And is there a risk that in the end, in your daily life, you see possible applications everywhere?
Well, the easiest one was maybe during the pandemic, something I didn't talk about. During the pandemic, the government sent a general call to all scientists. If there is something you want to do, tell us what you want and we'll give you a little money. And we had some random graph and empirical data on graph contacts in school, which we used to try some strategies for COVID modeling. So this was kind of pushed from the government. In terms of the glass ceiling effect, this is really from one of my co-authors. One day, we were both at the conference. He said he wanted to talk to me. I was leaving the next day, so we met over breakfast. And over breakfast, he told me that he was interested in sociology and he wanted to model the glass ceiling effect in social networks. And then we discussed how that could go and how one could model mathematically this and that effect. And so by the end of breakfast, we had a rough sketch of what we might do. So it's kind of a chance, I would say. And then years later, I thought he had asked me because I'm used to doing analysis of algorithms, but actually he had asked me because he had seen me participating at round tables about women and women in science, and so he thought I was particularly attuned to that.
Okay. Yeah.
So that was this one. The one for college admissions, I happened to be teaching at Collège de France. I was teaching the Gale-Shapley algorithm. I heard the government was planning to redo its platform right at that time, so I contacted them. The one about demonstrations, the idea just, it just occurred to me. It's natural, right?
Yeah.
And so it's just, I don't know. It just happened if you have your eye out for it.
Yeah. And what would be the next project then?
Next project. Well, okay. I think right now my main worry is how to do college admissions in a decentralized manner.
Sorry, how to do
college admissions in a way that is decentralized, or maybe how to organize, public policy if you're thinking of the possibility of an adverse government in the future someday. How can you plan for that? That would be my main direction right now.
Yeah. Okay, and I see Andy has a question. And for others
yes, I
as
do.
well,
I
please
do
raise your hand if you have questions. Yeah.
Okay, so very nice talk. I really enjoyed that one. So all your algorithms are you can call them white box algorithms, yeah. So they're very you can really understand what's going on there. Whereas we currently see a shift towards more data-centric algorithms. So how does that affect these kind of works? How do you see that if you want to analyze these kind of mechanisms, which are of course, harder to analyze?
This was the elephant in the room, AI. I didn't talk about.
Exactly.
Yes. Well, okay. I have thought or worked a bit on things such as detecting bias. So some questions around that. I have a former student of mine, Vincent Conadad, is working on trying to do mathematical proofs with Gemini, so making things a bit more, a bit whiter in a way. So I do think that without going inside the box, we can try to add some things around the box to try to at least preserve the guarantees that are currently cast in the law. Currently, legally, you're not allowed to discriminate. So, checking, how do you check for discrimination? How do you verify? How do you prevent it? All these things, these are, there's a lot of work on this. There's a whole conference on this. And, I guess this is not so much my area of expertise. I'm more of an old-fashioned algorithms researcher. So that's why I talk about the examples where I want to understand what's going on, because I feel whatever we do that implies the public has an impact on people, they want to know that they're treated fairly. They need to, there needs to be some amount of transparency. Why? So that they understand why they are, whatever they get, why do they get that and not something else? So, so that usually is much easier with white algorithms, white boxes.
Correct. Yeah. Thank you. Thank you so much.
And I'm looking if there's any other questions. Otherwise, I think we should thank you for this very interesting talk. And for those in the audience, I would like to tell you that our next colloquium will be on April 7, and then Peter Wenning, who used to be the CEO of ASML and has written the report on our innovation climate, will give a talk and will tell us what he thinks that we as computer scientists should do to improve the innovation climate in the Netherlands. So I hope to see all of you there. And I would like to use this opportunity to thank Claire once more. So many thanks for giving this interesting presentation.
Thank you, Claire.
It was a pleasure.
Okay. Bye-bye.
Bye.
Yes. Bye-bye.